Hello grade 11s. Today we study a force which affects our lives a lot. Friction. Friction plays a very important part in motion. Without friction, we would not be able to walk on level ground. You will find this out very quickly if you ever try to walk on ice. Before we get into the details of friction, let's ask Nelly how we adjust amounts of friction to meet our needs.
We maximize frictional forces when we use them to do work in stopping something moving. In situations where we require speed or where friction can damage the actual surfaces that are interacting, we would need to minimize friction. The first and most obvious way of doing this is to smooth the surface and polish them. But there is a limit to the amount of smoothing and polishing that can be done, and sometimes we need quicker methods of reducing friction. Oil acts as a lubricant between surfaces. Frictional forces are drastically reduced by lubricating the surfaces. Ball bearings also reduce friction. Cars and bicycles make good use of ball bearings, as do many machines. Even the hand-powered egg beater in your kitchen makes use of ball bearings to reduce friction. Essentially, we minimize friction so that we don't waste too much energy. Machines transfer energy to do useful work on things. If too much energy is used to overcome friction, this reduces the effectiveness of the machine. For example, if you forget to put oil into your car engine, it will seize up and require a complete overhaul.
Well, that's quite scary. Clearly, friction is a very important force which affects our everyday lives. But what exactly is friction? Here are two surfaces which move over one another and exert the force of friction on one another. Friction is a force which resists motion, and friction results when surfaces rub against one another. A man pushes a box which is on a table. The surface of the box and the surface of the table rub against one another to cause friction. Why? Let's imagine that we'll look at these two surfaces under a microscope. The surfaces are not smooth. They have jagged points. As the surfaces are pushed against one another, the jagged points of the two surfaces hook into one another. This happens even if both the surfaces are still, in other words, not moving. That is why there are two kinds of friction. Nelly, please tell us about these.
The type of frictional force that has to be overcome to start motion is called static friction. And the frictional force that has to be overcome to stop things is called kinetic friction.
Thank you, Nelly. Let's examine these two types of friction in more detail. Back to the man who pushes the box which is on a table. Here is a free body diagram for the box. We want to focus on friction, which is a horizontal force. So we'll simplify the diagram. We show only the horizontal forces on the box. We can simplify this further, like this. The man starts to push on the box very softly and gradually pushes harder and harder. What will happen? Let's draw a graph of what happens to the friction force between the box and the table as time passes. As he pushes harder and harder on the box, friction pushes harder and harder too. All this time, the box does not move. It is still. Another word for still or stationary is static. The table exerts static friction on the box for this time because the box remains still. The magnitude of the static friction equals the magnitude of the push by the hand while the box is still. We simplify these labels like this. Fs means static friction. Notice that the magnitude of static friction increases from 0 as the man pushes harder and harder. The two forces increase at the same rate while the box remains still. Then, at a certain point, the box starts to slide. When does this happen? This happens when the push by the hand has a certain magnitude called the maximum static friction for this particular box and table. Fs max. This is the maximum frictional force that it is possible for this table to exert on this box. Actually, the man needs to push a bit harder than Fs max to cause a slight resultant force to accelerate the box in the direction of the push. We show Fs max on this graph like this. Just after the box starts to slide, the man has to push less hard for the box to slide at a constant velocity. The box now moves, so the word static no longer applies. The word kinetic means moving. The table now exerts kinetic friction on the box. The force the man exerts on the box is now equal in magnitude and opposite in direction to the kinetic friction exerted by the table. We simplify these labels like this. We write Fk for kinetic friction. Notice how Fk remains constant as the box slides. This can be seen on the graph. Just after the box starts to slide, the magnitude of friction decreases to a constant value. This is the magnitude of kinetic friction for this particular box and table, Fk. Notice that Fk is less than Fs max. So surfaces exert less friction on one another when they move relative to one another than when they are still. Why? When they are still, the jagged pieces hook into one another a lot as they are pushed against one another. But when there is relative motion between the surfaces, the jagged pieces don't have time to settle down into one another as much. So kinetic friction is less than maximum static friction for any particular situation. Notice also that static friction can vary from 0 to Fs max, while kinetic friction is constant for any particular situation. It's obviously important to know the factors that affect the magnitude of friction. Nelly tells us how we could do our own investigation about this.
Set up an apparatus to carry out your own investigation of frictional forces. You can do this by attaching a rubber band the center front face of a block. Also attach a short ruler to the front face of the block near the rubber band so that you can measure the amount of stretch in the band when a force is applied to it. It is useful to mark the unstretched length of the rubber band on the ruler. Put the block on the tabletop and stretch the rubber band until the block starts to move. Mark the length of the rubber band on the ruler. Measure the stretch of the band. Repeat this procedure a couple of times to get the average stretch of the rubber band when the block starts moving. Try different ways of reducing the friction on the tabletop. Take readings of the amount of stretch of the rubber band under these change conditions and use these to decide what the most effective way is to reduce friction between the block and the surface.
Thank you, Nelly, and that is all for today. We'll leave the issue of how to solve problems about friction for another time. Also remember the task video for this series, and why not visit the Mindset website at www.mindset.co.za/learn. Until next time, goodbye.